my watch, so that way I remember, like, okay, find a stopping point.
Okay. All right. Well, good morning, 15th of October. We're going to do some R programming. Welcome back, Dr. Whitney Worley from the mathematics department at UCA. And we are recording to the cloud, so I'm going to let you take it away. You are fully in charge.
All right. So I am going to go ahead and start sharing my screen. I will, what I'll do is I will open up the chat. So if you have a question, feel free to stop me. Um, and then everything that are in my notes assumes that you have R and RStudio downloaded. So I will quickly show you how to find those if you don't already have those installed. So let me get started here. All right. And chat is open, so if anybody has a question, feel free or just butt in. All right, so like I said, everything that are in these notes assumes that you have R installed and RStudio installed. RStudio is a graphical user interface for R. It's much more user-friendly than trying to work in the R console. So once you have R installed and RStudio installed, you don't have to open R again. You can open RStudio and it will run R in the background. So to download R, you do have to install both. You can come to Google and type in R and CRAN, CRAN, and that will give you the information for installing R. So it's always the first link, and there are installing or downloading information for Windows and for Mac, or you can just click on that link and it'll say download for Linux, download for Mac, download for Windows. And you pick whichever system you have and download the most current version. This is the easiest way to keep up to date as well. R does update, and that is one of my downfalls of R in my slides, is that it's constantly getting updated. So every couple of months I come back in and check out. I actually know that I am not running the most current version because it just came out this week. So it is always nice to kind of laugh and look at what their names are. Their names are always ridiculous. So I am not currently running Bunny Money's Freakout, but that means I need to update. I try to at least stay on, if I'm not on the current version, I'm on the latest version. So just check every couple months if you're using it regularly, or if you haven't used it in a while, there's probably an update. Just come back in, you reinstall it, and installs over itself. RStudio, you can Google just RStudio as one word, and there is a link there to open. There's also a download link. But if you open it up, you can see all this information about RStudio itself. Most of the time, I either just click the download link there or I click it here. And then it says choose your version. You're going to want to be in this RStudio desktop free version. You do not want to pay the commercial license. So make sure you're clicking this first download link. It's free to use. And there is a server version where you can use it via the browser. I personally don't use this and don't know many people that do, but it is an option if you want to be able to use RStudio through the server and work with it in your web browser. Both of those are free. All right. So that kind of gives us an introduction to what you need to have installed in order for this stuff to work. And let's actually get started on understanding the language itself. So let's do a little background first. So what's the purpose of this seminar? Well, the main purpose is to talk about R's functionality. We're going to focus on data analysis, so I'll actually cover some statistical tests, how you would run those in R that you've probably seen or talked about at some point. So we'll focus on how would I actually do analysis, whether it's graphing, testing, whatever it may be. So we're going to talk about how to interact with R through RStudio. We're going to talk about some R coding, like how the language actually works. How do we import, clean, manage, and export data? So that's always important. Some simple data analysis, basics of two different R graphical systems. We'll talk about two different ways to produce graphs, and then how to use R to share your data analysis with others. So we may not get to that last bullet point, but I have included it in case in case we don't get there, it's some really good information and kind of like a next step once you get past all these other objectives. And then there will be these green boxes throughout, and what those are kind of a practice for you. You can think about the green boxes like exercises, and Dawn does have the key for these. So if you wanted to practice, there is a key for those that you can go in and check your work. So what is R? R is a programming environment for statistical computing and graphics. So what can it do? It can serve as a data analysis and storage facility. So we're keeping all of our data in R, and we're doing all of our analysis in R. We can perform operations on both vectors and matrices, which is really nice. So you can do univariate analysis or multivariate analysis in R. It uses a well-developed simple programming language. So it's built on top of a language called S. So it runs fairly simply. It takes a little bit of practice and getting used to, but it's not that difficult once you've used it for just a short period of time. And because it's free and open source, there's always rapid development of new tools according to user demand. With the Comprehensive Archive Network, that's what the CRAN stands for. There are all these packages that are constantly being built and submitted. You also have packages available through GitHub that people didn't want to submit to CRAN because CRAN has very strict updating rules and rules on vignettes, like your help menus and things like that. But there's all these different packages that are constantly being built to do all these new data analysis techniques. So it's really, really nice because anything that's being done currently, there's probably a package for it, or there's somebody currently developing a package for it. So why should we use R or why shouldn't we use R? Some of the advantages, it's free, and we love free. We don't want to have to pay for software if we don't have to. There's a big online community of things to help you learn R. So there's a lot of free online books, and there's actually a hyperlink here to give you access to some of those. So this is the Bookdown page. Bookdown are actually books that are built with R Markdown, and these are different authors that have made their books actually free to you. So there are all these different textbooks, and I will mention some of these later on as well. But one of my personal favorites is R for Data Science. I am a big component of anything that Hadley Wickham writes. He works for RStudio, excellent author, and really understands the language. So that's actually one of my favorite starter books, and you can access it online for free. There are also really powerful graphic systems that make it really easy to produce publication quality graphics. So not just a sketch or something that's really rough, the graphic systems in R create all those graphics that you would see in any type of statistical journal, any type of research, and they're fairly simple to use once you get the hang of them. You can create data analysis reports. You can create documents and presentations with R Markdown. These slides were built with R Markdown. So that I built all of these in RStudio, which is really nice because I can build my code in, any graphs that I'm building, I can also build those in a document. Also, I sent notes in just a classic HTML format where it just looks like a web page, and a PDF. All of those were generated with the change of one line in R Markdown. So that's really, really nice. And there are also, as I mentioned before, there's all these specialized packages that feature analysis tools that may not be available in other software because they're not being kept as up to date or edited as much. This is one of those places where R, when you're talking from a statistical standpoint, where R is better than SAS. SAS is great because it's so consistent, but it's not being edited very often. So for the classic things that you do every day on a regular basis and over and over and over again, that's one of those languages that is wonderful for people like the FDA who want to make sure everybody uses the same software and nothing is editable. For any type of new research or discovery for your job, things that you may need to write your own code for, R has a massive advantage there because of all these packages and code that other people have built for you that you can then access. Some disadvantages of R, There are some times that it can be more difficult to master than other statistical software just because it's a functional programming language and it's a little different. Some people aren't used to that. And as I mentioned frequently, you want to constantly update it. Those frequent updates require you to maintain your system. So if you don't do that and you're running on a version from 2 or 3 years ago, odds are your code's not going to run. So just make sure you keep everything nice and up to date. So RStudio, what is RStudio? You can work directly with R. So let me see if I can get, I was going to show you the difference between the two. You can work directly with R, but the thing about R is that it's not the easiest to use when you use R directly. So I've got both of them opening. I'll show you the difference between the console. So RStudio is actually called an integrated development environment. It's got all of these different sections and window panes that make it really easy to use. It's got a console, basically a place that you can write code directly. It's got a code or script editor, which allows you to write code and then run it from that console and save that code for future use. Where if you're just running it in the console, when you close R, it goes away. It's got special tools for plotting, viewing our objects and your code history. So you can actually view your plots directly in that image rather than having to pop them out like you would in R itself. And then there are cheat sheets included. We all love cheat sheets. There are cheat sheets that are included for our programming, and it has another option that's called tab completion that is super duper helpful. So this is what base R looks like. So you have to write all your code in this little window. And then if you wanted to write code that you could save again, so this is just writing it. When I close it, it would go away. If I wanted to write code that I could save, I have to build a new document, and then it builds like a text file, and then I've got to copy it and run it, and it's not all in the same window. And then if I wanted to run graphs, I'd have another window for that. So everything is running in these separate windows, which if you're like me, you can't stand. Now this is what RStudio looks like. Let's get rid of that. So here is what RStudio would look like. So you can build a script up here. So I can type code up here. So I can type my code, I can run it. It'll run down here in the console. If I were to build a graph, it would pop up in this pane over here. And if I expand this pane, I can see my working environment. So I can see that I ran X and X now exists. I could run Y. And now I can see that Y exists. So I know what code I've ran and what is stored in my environment and what I can recall, because I can see this all in one screen. So it's very, very nice for that. So this is why most people I know highly recommend using RStudio versus using R in its base form. So here's some more on the console. You can input or execute commands directly in the console. By default, that was this bottom left-hand tab, and it's labeled console there. You can rearrange these. If you go into RStudio and preferences, you can rearrange them. I know a lot of people, especially people that look at a computer all day, really like things to be in a darker format rather than this bright white, which I'm classic. I like the bright white, but if you like the darker colors, you can actually change all that in preferences as well. You can also change your colors if you are colorblind. That's really nice. There are colorblind options in there as well. Outputs of commands will typically be displayed in the console. So if I run a line of code and I want it to actually print the result of X, I can ask it what's in X, press enter, and it shows me that X is a vector containing the numbers 1, 2, and 3. So it prints all of your results down here. Even if you run the code up here, it prints down here to show you that it's ran. So the RStudio console features tab code completion and will help for function coding. So notice it says type RNO into the RStudio console and wait a second. And when a window with RNorm appears, hit the tab key. So when I say tab completion, if I type RNO, notice that it's going to pop up any functions that exist in packages that are currently loaded. So by default, you have a few packages that are already loaded for you. 2 of those that are the most used are base and stats. And there is a function there to generate random normal values. So if I click tab, it will fill that in for me. So tab completion makes coding so much faster if you know what functions you're needing. So remember, starting in this screen, these are suggestions for you to build your own R script and create your own like practice document. So if you wanted to start doing these, you could do file in your RStudio window, new file, and most of the time you're going to be working in an R script, and that will generate a new blank page, just like what I've shown you here. Now the cool thing about R is now I can save my code. So you can either click save here or go into file, save as, and store this somewhere that's useful for you. The other cool thing is when I reopen it, notice that this wasn't saved. I can close it and reopen it and it will still be there. I suggest saving, but if for some reason RStudio shuts down on you, it should still have anything that you've written in the script or the majority of it saved, even though you haven't saved it as a file, which is really nice. And I've also got other document types up here. Here's actually a copy of what your notes look like. So all of that is in here as well. Now it says once you have that RNorm function name completed, if the cursor is inside of those parentheses, RStudio will remind you of the function's arguments in a window. So you can also hit the tab key to see and issue the function argument names. So when I'm talking about an argument, I hit the tab button and it tells me these are the things that I have to include in order to generate random normal values. I need to know the n, or the number of values that I want. I need to know the mean for that normal distribution, and I need to know the standard deviation for that normal distribution. So not only is tab completion great for completing the name of functions, it also helps you remind you what arguments or parameters you have to put into that function to make it run. And then if you complete this line of code, it says place the cursor inside of RNorm, hit the tab key twice, and then type the number 10, hit enter to execute the code. You will generate 10 random normally distributed values. And notice that that doesn't say to put in, it did not say to put in a mean and standard deviation. Notice if you're typing up here in the script rather than the console, it will show you if there's any of those necessary commands that have defaults. So this is defaulting to a normal with a mean of 0 and a standard deviation of 1, or what we often refer to as a standard normal. Now the RStudio script editor, that's where I was just at. So most R programs written for data analysis consist of many commands. So if you were going to do this in the console, you're going to have to enter this line by line, and it's really, really inefficient. So instead what we do is we use that script editor to save our commands. Also, it's nice because I can come back in and start off where I left off working. The script editor features tab completion just like the console did. It also has syntax highlighting. So if I can like double click on X and it will find anywhere else the variable X is listed in my code. So that's really nice. So there's some instructions here again on how to go in and generate your own R script. And then how to write some other lines. So just remember, these are just little exercises for you. And you can execute code directly from the script editor. You can place the cursor inside of the command, or you can highlight the entire command, and then you can press Control Enter if you're on a PC, Command Enter if you're on a Mac, and run those lines directly. So that's how I was doing this here. Rather than clicking Run, I can just click. For me, I'm on a Mac, so I'm clicking Command and Enter, and there's 10 randomly simulated values from a normal distribution with a mean of 0 and a standard deviation of 1. I can click Run on that line as well, and it will run that line, which I don't like to use my mouse if I don't have to, so I try to use those keyboard shortcuts, or you can highlight it and run it. The highlighting is really nice if you're going to run multiple lines. So if I wanted to run these 2 lines, I can either press Command Enter twice, or I can highlight them and press it, and notice it runs them basically simultaneously. It'll run the lines in order, but it will go ahead and continue to print results for every line that you run. That is a really, really nice option if you've been working on code that builds off of previous lines and you've got to shut it down. It's time to come back to work the next day. You reopen it. You basically just run everything that you were working on the day before and pick up right where you left off, and it adds everything back to your environment. Make sure to periodically save your scripts. You don't want to lose any information, and most of those are saved with a .r extension. So the file type is actually .r. If you open a script, sometimes by default, it will open in R. So you want to make sure you go in and set those to open in RStudio rather than in R. So the environment pane, that is that pane I was showing you at the top right. It stores both the data and the output from the data analysis, as well as everything else in what are called objects. So if you notice here, it tells you here's the values. The values are the labels for the object, and then these are the objects themselves. So right now I have 2 integer vectors. They are both of length 3, and this one contains integers 1, 2, and 3, and this one contains integers 4, 5, and 6. Now, one thing you'll notice, you can assign or store objects using what looks like an arrow, so it's a less than sign and a subtraction sign, or you can use equal to. I highly, highly deter using an equal sign, and that's because equal signs also have other uses in R. This combination of the less than and the minus that looks like an arrow, that's actually referred to as R's assignment operator, so that's what you will see me use. Equals works quite a bit of the time, but there are times it will give you problems. So stick to using that assignment operator. It's a better option. Now, once we create an object, it'll pop into that RStudio environment pane in that top right corner. And then if you want to print the contents of an object, all you have to do is specify its name. So you saw me do that a moment ago. If I want to see what's in X, I just type the name X and it'll spit out its result. If I want to see what's in Y, I can just type the name Y. Now, where can you get help for R in RStudio? So understanding what's actually going on in RStudio itself. If you need additional help with that, there are documents that exist in R that will help you with both R and RStudio. The RStudio cheat sheets are amazing. They're just compact documents that are crammed full of information. So the way that you find these is through the RStudio help menu. So you can come to help, and you can come down to cheat sheets, and the very first one is for the RStudio IDE. So you can click on that and it will open the document up. And sometimes it will, with this one, what it decided to do was put it in your downloads folder. And it is a PDF document full of information on how to use RStudio. So everything is arrowed out and tells you what each button does. So it's a little bit of, it's a little bit jam-packed. I understand that. It's a little hard to read the first time. Once you get used to it, it's really nice. These are all actually made, all these cheat sheets, where you can print them front and back and have a single piece of paper for anything that you're looking for help for. So I always like that. I think that's really nice. I actually keep a lot of these in my office for things that I may not use very often and might need a reference for. Or I use these a lot with my students as well. And the other cool thing about this RStudio cheat sheet is it's got all these nice keyboard commands for you. So if you like keyboard shortcuts like me, this whole second page is just a ton of keyboard shortcuts. Trust me, I don't know all of them, but I know several of them. So find the ones that you need all the time and then reference the other ones when you need them. So how do I work with our packages? Well, I told you there are some that are already loaded in for you. Those are called base R packages. Most of the other packages you'll see used are available from the Comprehensive R Archive Network or from CRAN. That's where we went to download R. And if you want to go to CRAN and see what all is there, you can come here. Or honestly, if I'm looking for a new package or a test that I can't figure out how to use, Google is your best friend. There's all kinds of information online on using R, and there are forums everywhere where people talk about, oh, just use this package and this function, and there's actually so much documentation, you're overflowing with it. The basic packages that are already loaded into R deal with basic data management, basic analysis, and basic graphical tools. And we'll talk about some of those, and we'll also talk about more complex graphics as well. And as I said before, that's all nice, but the power of R lies in the fact that there are these thousands of packages. Currently, there's more than 15,000 packages that exist on CRAN that you can access, that you don't have to write the code for, and you can use someone else's expertise in writing the code to do whatever it is that you need to do in your analysis. So if I want to use one of those other packages, what do I need to do? Well, in order to put a package on your system, you only have to install it once unless it needs an update. But you're going to run a function called install.packages. Make sure you include that S. So the ones that I've listed here are actually 4 packages that I will reference throughout this seminar. There are plenty of other ones. The dplyr and ggplot2 are actually 2 of my go-to packages. ggplot2 is for graphics, and dplyr is for data manipulation. And they are honestly my bread and butter. So I highly suggest installing these 4, and they will actually coincide with things that I'll do throughout this set of notes. Now, I told you only have to install a package once. That is true, but you do have to library a package every time you want to use it. So the library says, I've got this package installed. I want you to go and pull information from it. By default, when you start RStudio, it is not going to have any of these packages libraried. So you've got to go in and put these in. So anytime I'm writing a script and I know I'm going to be using a package, what I do is I just add those packages to the top of my R script. And then when I restart R, I just rerun my package dependencies at the top and make sure that I've got them loaded. Otherwise, you may have things that don't run. Now, what is a vignette? I mentioned a vignette earlier, but I didn't go deep into what it is. What's a vignette? It is a style guide or a tutorial for a package. So it explains how a package is used. So it goes deep into detail on what's going on within that package. So if I load the vignette for the dplyr package, notice this will take a moment to run. So anytime anything's running, you're going to get a little stop sign here that says something's working in the background. And then notice this popped up over here in my right-hand pane under help. And it gives me all of this information on dplyr. One of the data sets that is loaded in dplyr is the Star Wars data set. It's always fun for practicing. It has all these information on different characters from the Star Wars universe. And it uses that to talk to you about all these different functions that exist in dplyr. It's actually not something I talk about in these slides just for time, but I will say if you ever learn how to use this pipe operator, your life in R will be so much cleaner. So I highly suggest that. And this is all talking about that information from dplyr in a lot of detail. If you want something a little shorter, there is also, if you come in here and check for cheat sheets, there's also a cheat sheet for dplyr, so a shorter version. So this is, the vignette is your detailed version, the cheat sheet is your short version. So let's look at some basic R coding. So remember, you assign things using the assignment operator or the equal sign. Again, use the less than and the minus, make the arrow. It's much more consistent. If you want to type a character string, you have to wrap it in either double quotes or single quotes. I, out of habit, use doubles. That's up to you. It really, those two things don't interact any differently in R. I just like double quotes. I don't know why. Now, commands can be separated by a semicolon, or you can just start a new line. Very rarely do I use a semicolon unless I'm wanting to run two very, very short commands on the same line. Most of the time you just click enter, start a new line, and that way it's more readable in the future instead of you not noticing that you actually started a new line there with that semicolon. One thing that is important, art is case sensitive. So you need to make sure if you put a capital letter in there, it's going to read it as a capital. It's different than if you put in a lowercase. So notice if I store a new vector, cap X, there's a default vector that's letters, that's the lowercase alphabet. So if I make capital X letters, notice that little x and cap X are in fact two different vectors. One is an integer vector of length 3, one is a character vector of length 26 that contains the alphabet. So just make sure that you're paying attention to that. It is important that you know what capitalization you're using. Because of that, most of the time I start all my commands with lowercase letters. It just keeps me from making mistakes. The pound sign or the hashtag is the way that we define a comment. Comment lines are not executed. So you'll notice if you look at the key, there are comments in the key that are all marked off with that comment line. And if you put a comment before a line of existing code and then you run it, notice when I ran that line, nothing showed up down here because it tells it to ignore everything after that comment. So if I do cap X is defined to be 2 to 6 and then put that after the comment, it shows it down here, but it's after the comment, so it takes into account the 2 to 6 and not the letters command. And the other wonderful thing about RStudio is it also color codes things for you. So some of these function commands like the library show up in blue, numbers show up in blue, comments always show up in green when you're in the default color settings. If you change your color settings, it will show you what would be a comment, what would be a numeric value, and so on. And commands can extend beyond one line. Ways that you can do that are things like plus signs, or if you have a big long function command, you'll see me do this in the future. I'll put a comma, click enter, and move on to the next line. So if the plus sign is on the end of the line, it will tell it go to the next line to finish off that addition. You cannot put the plus sign in this case before the 3. If you did 2, enter, plus 3 on the next line, enter, it's going to throw you an error on the plus 3 line because there was nothing to add it to. So it has to be at the end of a line for a multi-line command. So what is a function and what is the help file for a function? Functions are how R works. So we've already ran a couple of functions, one of those being the library command. The library command is a function. So you notice it opens and closes parentheses, very similar to what you've probably seen in basic algebra, right? So in basic algebra, you have a mathematical function that might look like f of x equals x squared. So you take an input x and it gives you the square as a result. Well, that's how R is working. That's why it's called a functional programming language. If you put a vector into the mean function, it's going to return the mean of that vector. So it's going to work just like a function would. And the inputs that we put in, I've already mentioned this, but not in detail. The inputs that you put in are the arguments. So for that rnorm function we were playing with earlier, the arguments were in, the mean, and the standard deviation. So that's what those should be referred to. Anything that you have to put in to make the function run. And then you can get help files for any of those functions by preceding the name of the function with a question mark. So if I wanted information on that rnorm function, I just do question mark rnorm, run the line, and notice it gives me all this information on what's going on. Rnorm is also related to these other functions. So when you deal with distributions, they always come in 4s. D's give you the density, P's give you the distribution function, Q's give you the quantiles, and R's give you random values. It tells you what the arguments are that relate to each one of those, and these are all put together because some of them are repeats. It shows you how that normal distribution values are calculated. It gives you some references. And then the cool thing about these question mark menus is they'll also give you a lot of examples. So sometimes those examples are useful, sometimes they're not. But for the most part, across a lot of these help menus, I use the example as much as I use the other information if it's a function that I'm not used to using. And then here's a breakdown of what I just showed you. The different sections are the description or the overview, the usage or the actual syntax, a description of the arguments, the details, which are actually telling you how the function is being calculated, the value, which is what the output is, and then some copy and pastable examples. Not all functions will include all of those, but they should include most of those if they are from CRAN, which anything that pops up in your help menu should. And then functional arguments. Values for arguments to these functions can be specified either by name or position. So if you don't name what you're putting in, remember when we were in that R norm 10, N was the first command, so it knew to put 10 in for the sample size. If you don't put the names in, it does by position first. So if we look at the log function, it says that the X comes first, the base comes second, and by default, it's base E. So here I'm actually naming them. I'm saying X is 100, the base is 10. If I could do this exact same function by just doing 100, 10 and not typing in the names. The key to typing in names is if you want to exclude arguments that have defaults, or you're not sure what the order should be, or you don't remember, but you do remember what the argument names are, and rather than looking it up, you just want to type them in. If you know the position, most people code based on position first. That's just up to the preference of the programmer. It's really just simply based on your opinion and the way you like to read it. Now, I told you that the equal to sign had other uses than assignment. The assignment operator is only used for assigning something to a name in R. This is one of those other uses of the equal sign, is to call the name of an argument. So that's one reason I don't like to confuse the two. Equals is always used in this scenario. The assignment operator cannot be used here, so just make sure you're careful with that. And then we also have vectors that we deal with it. So I've already generated a few different vectors in R. They're your fundamental data structure. They are one-dimensional and they are homogeneous. So when I say something's homogeneous, what I mean is they can only have a single variable type in that vector. So there are 4 common types that they can have. They can be illogical, which are trues and falses. Also, like underneath that, you can think about those as ones and zeros. They can be integers, which are integers only, meaning that you cannot put any other type of real number in that vector. They have to be integer numbers, and to type those in directly, you have to put in, you either have to use that colon notation I used a moment ago, or if you want integers that are not sequential, you have to put an L after them for R to know that you want an integer rather than just a raw numeric number. Other numeric numbers are referred to as doubles. Double meaning that it's doubles based on the fact that the number of decimal places that it's taking in. I'm not going to get really deep into why it's called a double, but basically you can think of double as a real number or anything that's numeric. But it is a real number. It is not a complex number. There is a special type of vector for complex numbers. I just don't cover those because they're not as common. And then anything that is word information is referred to as a character, and it consists of strings of letters or numbers, or from time to time special characters. So here, if you look at these examples, you've got an integer, you've got a character, you've got a double, and you've got a logical. So notice they're all different lengths, but each one of itself is of the same type. So these are all homogeneous. So how would I create a vector in R? The easiest way is to use the C function. C actually stands for concatenate. It's another word for combine. So it's basically saying take these values, put them into a single object together. So I can create a concatenated vector of the numbers 1, 3, and 5. You should notice that I did not include L's after these, so this is a double and not an integer, even though the numbers I put in you would consider integers. So that is a numeric vector. If I want to put in a character vector, I use the exact same function. I just wrap everything in double quotes. So these are some words as a character vector. And then a nice little function that we can use when we're dealing with vectors is the length function. It just tells you how many elements are in that vector. So the length of the character vector is 4 because I have 1, 2, 3, 4 strings. Another nice result is that you can use logical commands to get trues and falses based on some logical argument. So if I want to take this first vector and ask it, where is that first vector greater than 2? Well, 1 is not greater than 2, but 3 and 5 are. So notice if I run this logical vector or logical argument, it gives me a resulting vector of false, true, and true. So even though this started with a numeric, the result, because I used a logical operator, is a logical vector. We can also create vectors with a predictable sequence of elements. The way that we can do that is either with the REP. It stands for replicate. Some people like to think about it as repeat. So it's what you're going to repeat. You can also use SEQ to create a sequence of values, and then you've already seen me use the colon, which creates a sequence of integers. So all three of those can be used to generate a vector very, very quickly. So if I want to repeat a bunch of zeros, I just run REP, I put in what I want to repeat, and then another argument for that function is the number of times I want to repeat whatever vector I listed here. So if I want to repeat a 0 3 times, I do rep 0 and 3. Here I want to repeat the string ABC 4 times. So notice ABC is a string by itself. It's not a vector string, so it repeats the ABC string 4 times. And then sequence says go from the minimum to the maximum from the first value to the second value on the range that you tell it to go on. So that's the by argument. So if I say from 1 to 5 by 2s, it's going to go 1, 3, and 5. We're adding 2 each time. If you tell it to do a sequence on a number that is not a multiple of your end result, meaning if I said to go from 1 to 6s by 2s, it would still give me 1, 3, and 5, and there's no result at 6 because to keep counting by 2s, you'd have to pass 6. So be aware of that. If you're not using a correct multiple, it will not give you that last endpoint. You can also go backwards. So I can go from 10 to 0 by -5s, and it will count down. So notice I've got a larger value, a smaller value, and I'm counting in a negative fashion. I can do my colon operator, which we've already seen, just put a starting integer and an ending integer. If you want to count backwards, you just switch the order. So I could do 7 colon 3, and it would count down. And then you can also nest functions. So let's look at the way this is separated out. I can do a sequence from 1 to 3 by 1s. Okay, so 1 to 3 by 1s says 1, 2, 3. And then I'm going to repeat that sequence twice. So I'm going to do 1, 2, 3, 1, 2, 3, which is what we see here. And then I'll do these next two, and then I'll let y'all take a break. That'll put me at the end of a section. Other things that we can do is I can subset off my vectors. So if I only want certain elements from my vectors, I can subset using square brackets. So let's start by creating a vector from 1 to 10. And then here's a nice little trick. If you want to print a result and you don't want to have to type the name of that vector on the next line, you can wrap the assignment in parentheses. So if you run A assigned to be the sequence from 10 to 1 by -1s, so we're counting down, and then you wrap that all in parentheses, it will print your result. So we've got 10 to 1. If I want to know what is the second element of that vector, I take the name, I do open and close square brackets, and I put the element that I want in, so that's 2. So that tells me that the second element is 9, and we can verify that here because 10 is the first, 9 is the second. I can also subset based on a vector. So if I do a sequence from 1 to 5, notice I didn't put in that by argument. If you don't put in the by argument into the sequence vector, the default is by ones. So if I tell it I want the first, second, third, fourth, and fifth element, I can just do sequence 1 to 5 and it will spit those out. You could have got the exact same thing by doing 1:5. It would have given you the same thing for the first 5 elements. That's probably how I tend to do it on default. Or you can mix up the elements without them being in sequence and do any vector here. So if I want the first, third, and fourth elements, I can do that as well. And then I can also do conditional selection. So I can subset based on a value or a logical. So this is oftentimes known as logical subsetting. So let's say I have this vector. Let's say there's some sort of score. And I've got 55, 24, 43, and 10. Well, if I subset those based on a logical, it will only return the trues to me. So this is just to show you what it's going to return. So if I return false, true, true, false, or I subset based on that, it's going to return the second and third element, which are my 24 and my 43. The cool thing about this is it allows us to subset based on logicals. So if I ask what scores are less than 30, then that is my 24 and my 10, or my second and my fourth element. Well, if I want to subset that vector based on this logical, I just put the logical argument in the subsetting brackets that we used on the last slide. So say scores such that the scores are less than 30, so it returns the actual values from the vector rather than the logical vector, because this tends to be more useful than this. Okay, that's a good place to stop. Does anybody have any questions before we take a break?
I saw Allison with your hand up. You okay, Allison? I think she jumped out.
Oh, I missed that. I'm sorry. I was watching the chat and not the images.
It looks like she popped out. So, Jeremy, Janet, any questions before we take 10?
None here.
Okay, cool.
None for me.
Whitney, my brain, I mean, I'm a beginner Python programmer and with no intention of learning R because my brain just won't handle too much information. But it's interesting watching the difference. A vector in R is a list or a tuple in Python, and they can contain different data types. It looks like ggplot is matplotlib or Seaborn, and
well, there is actually a list element or a list object type in R that can contain different types. Vector is just the most base form.
Yeah. So yeah, it's just, I mean, it's like spoken languages. You know what I mean? It's just interesting watching the evolution of the terminology. Cool.
Yeah, if I have a second language, if I'm bilingual, my second language is R.
Well, I like it because it's the pirate's favorite language. R.
Yeah.
Okay, well, I'll pause recording and we'll be back at 10 after 10.
That works.
Cell phone time. All right.
I'm actually teaching a graduate level course in computational statistics right now. So we're doing all this at an advanced level. So this is kind of my everyday right now. All right. Let me make sure we're all up. Okay. So let's move on to importing and exporting data. So how do I get my data into R? Or if I'm manipulating that data in R, how do I export it back out and save it locally to my computer? So R is mostly going to work with data sets that are stored as some sort of text file, either a TXT or a CSV. Those are the most common. There are external packages to read in Excel files as well. But if I'm working with something in Excel and I want to read it into R, I honestly just find it easier just to save that file from Excel as a CSV and then read that into R rather than having to add external packages. R provides several related functions to read data in. So for reading in CSV files, there is a read.csv function, and to read in text files that has tab or space delimiters, you can use read.dlam. And read.dlim has an argument called sep equals for separator. So you can tell it whether it's a space or whatever that separator argument may be, if it's separated in some other form or fashion. They assume that the first row of the text file is a row of variable names. So it will read that in as the kind of top row of your table, where it's not actually data, but it's a variable name or a column name instead. If that's not true, you don't have variable names in your data, you have to add an additional argument that's header equals false. So by default, header is equal to true, saying that that first row is in fact your variable names. Although for this class, I'm going to have you retrieve a file from the internet, most of the time you're going to be doing this from a file that's saved to your computer or to your local disk. So this is kind of an idea on how we would do this. You're going to put in whatever you want to name your data, and then you're going to do read.csv, and then you're going to put in the path to that file wherever it's located on your computer. If you are if you wish, like you can get really detailed with this. I'm like to have all my things like extremely stored. So what I do a lot of times is I go in to the file itself and get the information off the file, and then I copy that path so I'm not having to type it in by hand every time. So a nice little shortcut that you can use there. Notice when I do read.dlim, again, I'm going to put in the path to that txt file, and then this is the command for making the separator a tab rather than just a space. And then here, for the rest of these files, we're actually going to use this data set from IDRE. It's a group at UCLA. So we're going to read that in. So you can, your path can actually be a URL. So I'm reading that URL in because the CSV file is actually on the internet. So I don't have to save it from the internet, then load it into R. I can just read it directly from the URL itself. We can export data to a CSV using write.csv. So if I have all the information, like I've edited my data set, whatever it is, and I want to save that where I don't have to do all the data manipulation that I've just done again, I'm going to use write.csv to export that. So you can save whatever objects you need to with save to generate an r.data file if you have multiple objects you want to save. Most of the time I don't use that as often. I tend to use this write.csv. So first you put in whatever you've assigned your name to. So that was the name of my data frame that I generated on the last slide. And here's the file. That's the path that I want to save the file name to. Rather than locating it, it's putting it in that location on your computer. There are also some additional packages for importing data from other software. As I said, you can read in Excel files. There's a package called readxl for that. There's also a package called Haven that allows you to read in data from Stata, SAS, and SPSS. And then one of the most common packages for reading things in is the reader package, or readr. And it has updated versions of read.csv and read.dlim. Instead, there's underscores instead of dots. And those use modernized data structures, and they actually run a little faster than the classic read.csv and read.dlim versions. I'll show you another little trick. If you want to import a data set from your computer and you don't want to have to type the path in, you can actually do import, and then most of the time I do from text and then readr. From Excel will automatically load that readxl package, and then these will automatically load Haven. So if you forget what the package is, don't worry, come up here to your environment, click import data set, and then a lot of times I click that from text readr, and then I find the location. So this can either be a file name, notice, or a URL, and then I can do all of this editing and it will write the code for me. Most of the time I close that open data viewer option just because that generates a big visual table that most of the time I don't need. And then when you're done, you click import and it will run these lines of code for you, which is nice. Now, when we import that data, what object type does it take? Because all these different variables are not necessarily going to be of the same type. So it's not just reading in one long vector, it's reading in multiple columns of information. So it's actually generating a data type called a data frame. They are rectangular. The columns represent the variables, and each row represents an observation. So you can think of columns as vectors. So each column has to be homogeneous. The overall table is heterogeneous, so it can contain different types within the data frame, but each column has to be the same type. So here, name is my first variable. So that this is a character vector. Weight is a numeric, height is a numeric, age is a numeric, and whether or not they have this disease of interest, that's a logical. But notice each row is an observation, so this row contains all information on the same subject, in this case John. This row contains all the same information, all the same type of information, but instead of for John, this information is for Emily. So that's a key to the data structure in R. Columns are always variables, rows are always observations or subjects. Now, what if you want to view the data frame? Now, like I said, most of the time I don't use this unless I'm really needing to look at things in really close detail. There is that function that I just showed you when we did import data set that's called view with a capital V, and it allows you to view the information in R as like a big table. So I'm gonna load a data set that is in R, that's just stored in one of the R base packages. This is the MT-CARS data set. But if I type view and the name of whatever data frame I'm wanting to look at, notice it has if it has row names, it inputs them over here. If it has column names, it puts them at the top. And then it puts all this information in for you where you can scroll around and look at it, similar to what you're used to seeing in Excel. But it's not, notice it's not editable. Okay, so you can't do any manipulation here. What you can do though is sort based on a column. So you notice these little arrows at the top. So now I'm sorting by horsepower descending, horsepower ascending, miles per gallon ascending. So you can look at things that way, which is nice and pretty easy. And a lot of people that are new to R like that view option. Once you get more practice, you'll probably use that less and less. Now, this is actually one of my go-tos, or these next two options, is to just get a glimpse of the data. So not the whole data set, but just to kind of see what's going on. You can use one of these two functions. They are head and tail, not heads and tails. There are no S's. But head will give you the first specified number of rows of the data frame. So it will give you, in this case, in this example I've done, the first 2 rows. And tail will give you the last set number of rows. By default, it gives you 6. So if I just do head of my data frame, close my parenthesis, it will give me 6 rows. So all you have to do is type that in with the name of a data frame, and notice it prints it right here in your console for you. I tend to find this a little easier, and then when I want to do manipulation, I use all that information from dplyr, that package I mentioned earlier, and I'll hit that some more in a moment. Just like we talked about subsetting vectors, you can subset data frames using square brackets. The key now is, though, that you have an additional dimension. So you have to include rows and columns rather than just the location within the vector that you want to subset. So rows comes first, columns come second. That is based in the way that matrix multiplication is done. You do rows by columns. So everything tends to think about rows as dimension 1 and columns as dimension 2. So suppose that this is my data frame. So I'm going to build this by hand. This is the first time we've built a data frame by hand. So I'm going to put in 3 patients, Smith, Jones, and Williams. I'm going to put in their height, 72, 61, and 66, and whether or not they're diabetic. So true, false, and false. Now, if I say I want my data, row 3, column 2, so row 3 would be the patient for Williams, column 2 is the second variable, so that should give me the height for Williams, which is 66, which is exactly what we see here. And if you look at this and actually print this out, let me copy that and run it over here. If I run that view function on it, notice I'm going to row 3, column 2, and there is where my result is coming from. Let's say I want the first 2 rows of the column height. So I can subset based on names if I have a named variable, and I can also include a vector rather than just a single value. So this is going to give me the first 2 rows or the first 2 values in the height column. So it's returning the 72 and 61. Now notice, because I'm only returning a single column, if either one of your dimensions that you're returning is 1 dimensional, it will return a vector. If you're including anything that's 2 dimensional, it will return it as a data frame. So just be aware of that. And then another trick we can do is we can return all columns or all rows. So all I have to do to return all columns or all rows is just exclude that dimension. So if I do my data, comma, I've excluded the row dimension. The column I'm wanting to export is diabetic, so it's just going to give me the information that we put in for that diabetic column. Another nice little trick is you can also pull out a variable using the $ operator. So it says pull this name variable from this data frame. So we put in the data frame first. So it says reference that, get the variable called height. So that's exactly what we're observing right here. So if I want the height variable, it's just going to spit this vector back out for me. And then from that, you can subset using the square brackets. So if I wanted the second and third values of height, then I take this information and just add my double square brackets after it, just like what we did in that last section. We can also add names to our data frame columns if they didn't already exist, or we can change them if for some reason we need to do that. So the way that we can see what our column names are for a data frame is just COL for column and the word names. So I can run call names on my data and we can see that I have patient, height, and diabetic. Well, in order to change those, rather than, I'm going to take that exact same command, but now I'm going to put the assignment operator after it, and I'm going to change my names because now I want to capitalize these. So I'm going to change them to patient, height, and diabetic with capital letters. And now notice when I run that exact same line of code, they have changed from lowercase to capital letters. And then I can also change just a single variable name by using indexing or subsetting. So I can say, well, what if I want 3 to be diabetes rather than diabetic? I can change just that one by subsetting with that square bracket 3. And now notice the first 2 remain the same. The third one has changed as we wished. Now, what if I want to look even deeper into the structure of an object? One thing that we may be interested in are the dimensions of an object. So if we have anything that's 2-dimensional, whether that's a data frame or a matrix, we can find the dimensions using the dim function. So the dimension of that last data set we were looking at was 3 by 3. We had 3 rows or 3 observations of 3 variables. If I want to look at the actual information of that data frame, so the structure of that object, including its class, what type of elements it contains, there's this str function for structure. Str is always really nice especially if you're looking at somebody else's data or data that already exists in R and you don't really know what's going on in that data frame. You can do str in the name of the data frame, and notice it says the class is a data frame, so it's a data frame, not a matrix. It tells you how many rows, that's the number of observations, how many columns, that's the number of variables, and then it tells you how to $ out each one of these, which is very, very nice. And then it shows you what type of vector that variable is. So this variable is a character, this variable is a numeric, so even though these look like integers, it is a double instead. And then the diabetes variable is a logical. So you can get that vector structure for each variable very, very quickly. You can also add new variables to an existing data frame. So let's say I already have that previous data set that I was looking at before, and for some reason I need to transform the height based on the log function. And remember I showed you a moment ago, the log function's default base is log base e, so this is actually the natural log of the height. So if I wanted to do the natural log of the height and add that, I can do my data $, I'm putting in the new name that I want, and then I'm assigning that to whatever calculation I want on that previous column. And the one thing you need to be careful of is each vector or each variable has to have the same number of observations. So you've got to make sure it's the right length. In this case, because you're doing a calculation on an already existing variable, you can guarantee that the two vectors are going to be the same length. So that's good. Now notice when I run call names, it's showing this new column name that I created right here. This line though, however, it won't run. So if I create, remember we said the repeat function or the replicate function will generate whatever you put in first, however many times you put in for the second object. So it's going to create a vector of 5 zeros. If I try to run this line, it will generate an error because my data has 3 rows, not 5. So it will tell you this is not the right length. You need to do something different. So it'll give you a little red error, and it will not add that on to the end. So there are some multiple different functions you can use from existing variables. We've already looked at log. There is min_rank that'll rank your values. Basically, it'll tell you what order in which they fell. Cuts a continuous variable into integer or into intervals. So it'll create you some ranges rather than just raw continuous numbers. Scale will standardize your variable. It subtracts the mean and divides by the standard deviation, highly related to like z-score values, that type of standardization. Lag and lead, those are really, really nice when you're dealing with time series. So if you want to lag back 2 time periods, you can, or you want to lead ahead 2 time periods, you can. That's a nice little trick for that. Cum sum, these are cumulative sums. So building like binomial tables, if you're going to build them in R, this is a nice little way to do that. So what you can do is you can do cumulative probabilities really easy by adding up every probability up to that point in a vector. There are also row means and row sums, which will give you the means and sums of several columns. So it'll add across your rows for each one of those. Now, what if I need to manage my data? Like, what if I need to do some sort of calculation or reorganization, anything like that? Well, the first thing we have to do is we have to prepare our data to analyze it. This is one of the hardest things in data analysis, is making sure your data will actually do what you want it to. So the way that we can do that, or some ways that we need to do that and save ourselves some frustration and time, is first thing we might want to do is only cut the data down to the information that we're actually going to use. A lot of times you get a lot more variables than you need. So we can actually cut our data to only the information that we want. I may have 2 data sets that need to be put together rather than analyzing them separately. So we can combine those data sets. And we can also make sure our variable is free of errors. So such as things that are impossible, coding in anything that's missing, making sure that everything is as it should be. So the easiest way I know of to do this is the dplyr package that I mentioned earlier. dplyr is honestly like your best friend if you need to manipulate your data. It works specifically with data that's in that format we talked about a moment ago, these data frame formats where every row is an observation, every column is a variable. So in order to do what I'm going to do in the next few pages, you've got to make sure you've got that libraried in. So the dplyr has some different functions that will do things that are really useful. The first one of those is filter. So what filter will do is it just picks off the rows that satisfy some sort of logical. So you give it a condition and it gives you the rows that correspond to that condition. So I'm going to copy this code into our session. So there is my dog data frame. And we're gonna run that, okay? And then what we wanna do here is I want to find all dogs that weigh more than 40 pounds. So one way I can write that is I can take the filter function, I can put in the name of the data frame, and then I can put in the condition I wanted to condition on. So why did that not run? Oh, I've got to load dplyr. So you got to run the library line. Make sure you do that. I typed it in and didn't run it. So don't make that mistake. But notice now the only two dogs that weighed more than 40 pounds were Buddy and Daisy. Buddy is a male, Daisy is a female. Buddy's from the north and Daisy is from the south. So I got all that information in one quick line. Now this isn't in my notes, but I'm going to go ahead and show it to you because it is a dplyr user's best friend and it is called the pipe operator. So anything that I'm using in dplyr is going to start by calling the name of the data frame. So anytime I want to use a dplyr function, I type the name of the data frame and then I'm going to put in the pipe operator. It's percent greater than percent. If you are using a PC, the shortcut for that is Shift, Control, and M. If you are using a Mac, it's Shift, Command, and M. And then I'm going to put in the function that I want. And then run that. Now you may say, what's better about that? Well, the first thing is I want this data frame and this is what I want to do with it. So I'm not having to completely nest multiple things. The other cool thing about this is I can add additional arguments here. Like let's say I also wanted sex to be male. Now I can say, okay, I want the weight to be greater than 40, the sex to be male. And notice now that's cut out my second row for Daisy. Now I just have the information for Buddy. So I'm not constantly wrapping these things around each other. I'm just taking this line and I'm putting it into the first argument of this one. Now I've got a subsetted data frame, so I can put it into the first argument of this one, and it just continues to place things into the next line of code. So it's a very, very nice little trick, and this is actually a function that you get access to by using the dplyr package. Now, something else we could do is we can input multiple filters into the same line. So this one says filter out all of the female dogs from the north and south locations. So here is the way it is coded in the notes. And to do this in the pipe operator form, you just take your data frame, add the pipe, and then add your next line. So the way this reads, let me add, I missed a parenthesis there. So this says the location is north or south. So location is equal. If you wanted the logical for is equal, it's double equal signs. North, this vertical bar is your option for or. So the location is north or south. The and sign says and, so that's your intersection, and the sex is equal to female. So when you run that, you notice the only female in the north or south is Daisy. You can also subset variables using dplyr. So if I only wanted the variables ID and sex, I could do that using the select argument. And once again, the cool thing about that is I can do that with my pipe operator as well. And then I can say, let's say here I also wanted to filter that my sex is male, then that will only give me the names and of the male dogs. So once again, you can layer these in together, which makes data manipulation very, very quick and intuitive because you're thinking step by step. As if I was working with this data and I was doing all this by hand, what would my next step be? The base functions don't allow you to do that, and dplyr does. You can also use a negative sign to deselect any column. So if I wanted to leave these columns out, all I have to do is put a negative sign in front of them and list them as a vector. So now notice it would just give me the weights and the location. So it drops, it includes the columns that it dropped a moment ago. We can also append observations. So we can add rows. The way we add rows is using the rbind function. So here what's being done is we've just added a new information for 2 new dogs, Jack and Luna. And then notice we have the exact same column names. So all I have to do in order to add these on to my previous information is just rbind them. So I list whatever data frame I want on the top. So that says everything for the first 6 rows. That's all my previous data. The more dogs are my 2 new rows. So I've just added them on or tacked them onto the bottom, and I've given a new name to that data frame. So I've stored it again. You can, if you're wanting to add these on and keep your original name, you could store these as dog data and it would override your previous information. You can also add data by merging on a key variable. So in the dplyr cheat sheet, there's all these different options about how to merge variables. They're all called joins. So the way that you can join is, there's different ways that you can join. There are left joins, right joins, inner joins, and outer joins. But what those allow you to do is it matches variable names and then it combines the data frames that way. So here I have a second data frame with all my dog names, and then it has their vaccination information. Notice these names are not in the same order that we had previously, but they are the same 8 dogs. And so I'm inner joining all dogs based on dog backs. So what it's saying is I want to take this new data frame and I want to join it to all dogs. So it says take the all dogs and any new information that's in this data frame that wasn't in my original, which is my first 4 columns, add that on. So it's adding on this vaccination column, and notice it's matching them up based on the ID. And that's what it's telling you right here when it prints this line. It tells you it joined by ID because that was the common information between the 2. You also want to be careful with missing values. So a lot of times when there is a missing value in a numeric column, people like to code it in as a -99 or a -999, something like that. A dog obviously can't have a negative weight. So if I wanted to calculate a mean on the dog weights, I'm now in trouble because I have this negative value that's going to skew all my information. So I need to code that as missing rather than a numeric value. So what I've told this to do is take any location where I have a -99 for dog weight and replace that with an NA. So an NA is a missing value in R. It has to be in all capitals. And notice when I print my weights now, it has replaced that last value, which we added right here. Something you should be aware of is missing values are contagious. What do I mean by that? If a missing value is included in the calculation, the result is missing. So 1 + 2 + NA, it doesn't know what NA is, so it doesn't know how to add it in, so the result is NA. Here I'm taking the vector 1, 2, 3 in NA and checking to see if it's greater than 2. Well, 1 is not greater than 2, 2 is not greater than 2, 3 is greater than 2. NA could be larger or smaller or equal to 2. It doesn't know, so it's missing. Here's those dog weights we just had. If I take the mean of that, the mean is missing because once again, it doesn't know how big this number is, so it can't calculate that. So there are functions in R such as sum and mean that have an additional argument for removing NAs, and it's na.rm for NA remove. Just make sure that if you use one of these, you've reported that you had a missing value and had to remove it from your calculations so that people know that your calculations are based on only the information that you had. So here, if I do NA remove of this sum, then it's going to take the sum of 1 and 2 and give me back 3. Here, if I take the mean and remove the NA, it's the mean of the other 7 dogs that actually had weight measurements. Things you can't do is check for equality to NA because NA means undefined, so it will always give you an NA back. So if I have X is the vector of 1, 2, and NA, and I check is X equal to NA, then it just spits out a bunch of NAs. So it doesn't tell you where the NA values are. Rather than doing that, if you want a logical that checks for NAs, you can do is.NA of X. And it will give you false, false, and true. And I'll go ahead and hint at another little trick you can do. Trues and falses function as ones for trues and zeros for falses underneath everything. So if you want to find out how many NA values you have, you could wrap this in the sum function and it would spit out a 1 because there's only one true. So that's a nice little trick if you need to count something as well. You get a logical and then you count the number of trues. Okay, let's look at some basic data analysis. I will hint at some of this, and just for time's sake, I'm not going to go deep into all of these. But I'm going to point out some of these functions that will do calculations that you probably talked about at some point or another. There are functions in R for the mean, the median, and the variance, and also the standard deviation. And then summary is a nice little function that will give you a numeric vector, and that numeric vector is named, and it will spit out the min, the max, the mean, the median, and the first and third quartiles, and it will do them in ascending order. So here I've generated a data frame called blood test. I can do the mean of the ages and it will spit that out. I can do the median of the ages, the variance of the ages. I can do the summary results for test 1. And notice it's min, first quartile, median, mean, third quartile, and max. So it's giving me all of that information that would essentially be needed for a box plot plus the mean. I can also calculate correlations between two values, so I can see how linearly related two variables are by putting those into the core function. So here I'm saying, are the values for test 1 linearly related to the values from test 2? And I have a correlation of 0.77, so we would say that there's probably some linear correlation between those. And then I can use dplyr, for example, to pull out and test specific variables. So here I'm selecting from that blood test data the results for tests 1 through 4, and then I can create a correlation matrix which checks each set pairwise. So you'll notice that this matrix is symmetric over its diagonal. So test 1 to test 2 here is the exact same as test 1 to test 2 here. So that's the correlation that we saw. That's the exact same value we saw, right there. And then it does that again for each pair. And notice the diagonal is 1 because everything is always perfectly correlated with itself. So values close to 1 or stronger linear correlation, values closer to 0 are weak to no linear correlation. We can also generate frequency tables. And the functions for doing that are table and prop.table. So table gives me the frequencies. Prop.table would give me the frequencies expressed as proportions, or also known as relative frequencies. So from my previous data set, if I wanted to count people in the male and female groups, I just run table on the categorical or character variable that I was interested in. So it tells me I had 6 males and 4 females. I had 3 people at hospital CLH, 2 at MDH, and 5 at MH. And then if I wanted to look at those proportions, I have to take the table function and put it inside of the prop.table function. So essentially it's taking this table and converting it to proportions. So I had a 30%, 20%, and 50% in each one of those hospitals respectively. I can also generate cross tables or two-way tables, and you can generate multi-way tables if you have more than 2 categories. Two-way tables are just the most common. So I can generate those using the table function. So if I wanted to look at the number of people in each gender by hospital, I can generate a two-way contingency table of that information. So I had 2 females at CLH. And then I can put that, notice I've saved that to a name. So I can put that name into prop.table rather than the table function itself. And I can do either row proportions, column proportions, or proportions on the total. So if I add a margin argument, and I just realized there is an error in my code. This one should say margin 2. So make a note of that. But margin 1 says do proportions on the rows. So here's the row proportion. So the of females, 33% were at CLH, 17% were at MDH, and 50% were at MH. And then you would do the exact same thing for columns. I'm sorry, I used some copy and pasting there and I didn't change my margin. So here it would do the margins on the column. So it should say 67% of CLH patients were female and 33% were male. So it should be 67 and 33, 50 and 50, and then 60 and 40. Some other statistical analysis you can do in R. Pretty much anything that you've learned in an introductory statistics course you should be able to do, plus a lot more advanced things. So chi-squared test, t-test, correlations, covariance, ANOVA, linear regression, generalized linear regression like logistic or Poisson regression, time series analysis, statistical distributions, generating random numbers, densities, distributions, quantile functions, all of the above. So your normal distributions, your uniforms, your binomials, all of those you can do calculations on in R without having to use those formulas. All of those things that I just listed are available in the stats package. And there's even more in other downloadable packages. So here, I'm just for time's sake, I'm going to kind of breeze through this section, but you have calls for a lot of these common tests. So the call for a chi-squared test of independence is chi-sq.test. This talks about formula notation. So if I need to put information in a formula format, this is how we do it. We put the response on the left or the outcome and the predictor or the covariate on the right. And then these are different ways to add more than one covariate. You can also do independent samples t-test. So this is a 2-sample t-test for independent samples using t-dot test. And then if you have a paired 2 samples test, you just add a command for paired equals true. And in the output, it tells you what you ran. So here it tells you it's paired. Here it tells you it's a Welch 2-sample t-test because it's an approximation assuming unequal variance. If you have equal variance, you have to add an additional argument there. And you can get all that information from running !t.test. You can also do linear regression using the function LM for linear model. And with that, we put in a formula. So it's whatever variable I'm wanting to predict, whatever I'm using to predict that result, and then the data frame after the comma. So if I wanted to predict the result of test 1 based on age and gender, here's my coefficient for age, here's my coefficient for gender, and it tells me that that this is based on males, so it would make female the baseline. If you've done any logistic regression, then whatever is not included here is your baseline. Whatever is included is what it's basing that variable on. And then it also gives you the coefficient for your intercept. But that's not all the information you can get. So if I wanted more information from my linear model, I can run all of these functions to get additional information. The most common one to use is the summary function, just like we used a moment ago, to get that information from just a vector. Well, if you run summary on a linear model, it will give you the 5-number summary of your residuals. It will give you tests of significance, it'll give you tests of significance for all of your variables. So here it's suggesting that we probably don't need to include male. So I'd probably remove that and then see if age becomes significant. And then it also gives you the residual standard error, the multiple R squared for this model. So it gives you all this information in one nice little location. If you just want the coefficients, there's a function for that. Or 95% confidence intervals for the coefficients, you can get those as well. And what this is actually doing is using column bind to take the values, generate the predicted value, and then show you what the residuals are. So the predicted value would be the point on the line for this test. And then remember, the residual is the difference between the observed result and the predicted result. So this value for the residual is just 47 minus 38.76045. And then that's giving us this result here. Then we've got ANOVA. So if you want to run ANOVA, you just run ANOVA on your model. and it will give you the ANOVA table that goes along with that. And you can run two nested models into ANOVA to conduct the likelihood ratio test. So higher level regression, you want to compare models to see if adding additional variables is useful. And you can do that by putting both into the ANOVA function. You can also run regression diagnostics, generating plots that tell you whether or not your model is good. So residual plots, you want to make sure they're random. You want to make sure that normal QQ plot of your residuals is roughly straight. So here, this appears to be pretty random. This is pretty straight, so that's good. And then you also get these scale location and residuals versus leverage graphs that tend to be used in higher order regression analysis. There's a different function you use for logistic regression called GLM. I will just leave that there for you since we're running low on time. And then these are a bunch more packages that are useful in common statistical analysis. So I've put these in as a reference as well. Okay, now just for the sake of time, it looks like I'm not going to have a lot of time to go into graphics, but I want to point something out, and I'll just kind of go through what else is in here because I wanted to get you an understanding of the base of the language, which I thought was the most important. And then I added a section on graphics and a section on Markdown. So I'll kind of give you a brief description of what these are doing. So these first couple of sections are going through what base graphics can do in R. So these are the functions that already exist in R itself. And then, so these are all what are considered base R plots. And then I go into this section introducing ggplot2 for graphics. ggplot2 is my go-to graphic system. It's a little more complicated to learn, but once you use it, it's probably going to be the only thing you want to use. And the reason why is it has a similar structure to what we talked about with dplyr, that you can build line by line and layer things in. So with ggplot2, I can say, okay, this is the data frame. First, I want to build a graph, which is my ggplot argument. And then I can say, this is the data frame I want to build from. And then I add what are called geometric objects, which are whether they could be the dots, they could be a box plot, they could be a histogram. And so I tell it what shape I want it to build from that data. And then I can add additional layers for the labels. I can change the colors. So I can do all of these things that are really nice. And it's also really, really easy to add legends. So if you look at my notes right before this, adding legends is not easy in base R. It does it by default for you in ggplot2. So there's all these really nice little tricks, and everything is really nice and easy to look at, very eye-catching and easy to manipulate. So there are examples in here of scatter plots, and like here with a single line of code, I was able to add a best fit line through the scatter plot, which is much, much more complicated in base. I would actually have to generate the model and then add the model on, and then add a line for the model, and it's not very easy. And notice here I added a couple of little arguments, and I generated a best fit line for males and females separated, and it only took 2 additional arguments in my ggplot line. So there's a lot of really easy graphical things you can do that look really complicated in ggplot2 that make things really easy. And then what I can also do is I can also say this data set that I'm using here also split people based on what educational program they were in. So not only can I split into colors, I can also split using what's called a facet and separate out on another categorical variable. So now I've got all these different graphical pieces of information in a 2-dimensional graph that otherwise would be impossible. There's also all these neat things you can do with box plots. So here, this started out just splitting on program. And then I added the points and I jittered them just so that you can actually see all of them. So I've added all the data where you can actually see where the data is falling. And then I've split based on if their school is private or public. So we can see, like, especially in vocational schools, there's a massive difference in math scores for private schools versus public schools. And then I can also, so by default, R puts this gray background. There are also things called themes where you can change the background scales and what colors they are and whether or not they have a grid. So One of my favorites is theme_BW, which is black white. So I can make some changes like that. This one also goes into how you can very, very specifically change every little bitty piece, as well as adding titles and X and Y axis labels. So this gets pretty in detail with ggplot, and I highly suggest if you're planning on using R for anything, learning it. It takes a little bit of practice, but once you get it down, the graphics are so much better, so much cleaner, and they're easier to manipulate as far as like sizing the graphic and everything than a base R graphic. And then I'm just going to tell you what this last section talks about. It's about being able to share your work. So it goes into this idea of an R Markdown document. So I told you most of the time when you build a document in here, you're going to go to File, New File, and R Script. Well, there's also an option for what's called a Markdown file. And a Markdown file, oh, sorry, not a Markdown file. I said that wrong. You want R Markdown. I clicked the wrong one. So R Markdown will open up. It'll let you put the title in, your name, and it will ask you what kind of document you want. So you can build HTML, PDF, but you can only build a PDF if you have LaTeX loaded on your computer. That tends to be more math-related people that already have that, and it's a big download. So if you don't use it, you're not used to it, I wouldn't worry about that. You can also generate Word documents with R code in them, or R graphics, which is really nice. And there's also multiple different presentation types. Again, the PDF requires LaTeX to be downloaded, but you can generate HTML slides. The presentation that I'm doing for you, it's built in Slidey, and then PowerPoint as well. Now, the cool thing about this is this document that I built for you, this is my Slidey presentation. All I had to do to generate my notes for you in that PDF format was do PDF_document. Again, I have LaTeX downloaded. But if you wanted a Word document, all you had to do is change this output, and the code is the same for building this for all three different types. So it's really nice to be able to generate your work in multiple formats and to be able to share it with other people. So this goes into detail on the different things you can do. Some of the basic things like putting things in italics or bold, superscripts and subscripts. How to put code into that. So code chunks are where we actually type in all the code. So all those gray boxes you've seen are actually in what are called code chunks. So they look like this, and there's an option to insert those, or there's a keyboard shortcut for that. The YAML header. So YAML is yet another markup language. It uses Pandoc, and that's where I put in the information for my title, my date, what type of output I want. You can put your name there. There's all types of things you can do up there. And then there's also things that you can build in there that are called Shiny apps. Shiny apps are interactive, so you can create like sliding bars. You can create a histogram and have the sliding bar change the bin width, so you can see what happens as you adjust the bin width in that. And so I didn't have you, in this example, I didn't have you generate any Shiny apps. I had you look at some examples of ones that already exist, so that if you ever wanted to do that, it's a little bit more of a high-level R thing, but they're really, really useful if you need something really interactive for whatever you're presenting. And then I've put in some additional help for you. There's the UCLA Stack Consulting website. It has tons of stuff for statistical analysis. Stack Overflow, I told you there's all these message boards that people that use R talk on. Stack Overflow is our favorite, and there are just tons and tons and tons of conversations on just about anything you want to do. And then I told you at the beginning, there were all those books that you had access to. This is a direct link to that R for Data Science book that I was recommending. So if you click on this, it will take you to Hadley Wickham's website for that textbook. And if you get through this one and you're comfortable, he has a link in this for another book called Advanced R, which is R at a higher level. So it gives you a better understanding of what's really going on underneath. So this is a really, really comprehensive understanding of R for Data Science. And it includes things on Markdown, things on modeling. So very, very in-depth, and it has little coding boxes in it, very similar to what you just saw, that you can copy here and then paste them into your R Studio scripts. There's additional books on R that exist. These are not free online books, but there are books that you can use. So there's a whole link for that. So I will, if you have any other questions, I know I had to like breeze through some things, but I put those in as extra resources for you anyway. So if you have any questions, feel free to ask me. Other than that, thank you. I tried to squeeze it in as much as I could.
No, that was excellent, Whitney. I mean, just a whirlwind tour of R for people that are, are familiar with a programming language, and lots of resources to take it to whatever level they care to. To me, the biggest takeaway is just there's so many different tools out there. There's so many different ways to get the answers that you need, depending on the environment where you work and what your company really wants to focus their workforce on. Guys, Janet, Jeremy, Jeff, any questions for Whitney before we depart?
None here.
Nothing for me.
SurveyMonkey demonstration.
What was that last one? I heard the word demonstrations. Okay. Well, again, Whitney, thank you so much. Way better job than Kevin and I did on Monday. Much more thorough.
That's right.
You are a pro, and I sure appreciate it. Okay. Thanks again, and I'll be in touch with you on that other matter.
All right. I got
All
that
right.
information written down, so I'll try to get that to you soon.
Okay. Well, we'll see you guys 8:30 Monday morning for our last week of classroom material. All right.
Thank you.
Bye, everybody.